Okay, so welcome to your digital learning day. Today we are going to essentially continue what we started yesterday with going through some ideas of permutations, mostly ideas out of section 13.3. Just a quick note here, you should be watching this video. You should be filling in the notes that we're going to be going over here while you watch. Make sure you if you have any questions as you go along, feel free to pause and kind of bring it back, listen to it again. If there are some questions that you have about any of the material, just make some notes on the note sheet. We'll do that first thing Friday morning, tomorrow morning. So, and then in addition to filling out the notes, I would like for you to do these problems due for Friday. You should have done these for today, hopefully, off of the half sheet that I passed out in class yesterday. For Friday, for tomorrow, I would like for you to have a few more of those problems finished up, and then we'll talk about those also. And Friday, we'll just kind of, we'll have a worksheet that we're working on. No new content, really. I'm just kind of working on some problems together in groups in class. So what I'd like for you to do is to get out the notes that I passed out to you yesterday. There is a warm-up problem here. I'd just like you to think about questions A and B up here. And then we'll go ahead and finish this together. So feel free to pause. Actually, what I would like you to do, if we were actually in class, I would give you a few minutes to work on this. Obviously, on a video, I'm not going to do that. But go ahead and click pause real quick, and we'll come back together and go over these together. But give yourself the opportunity to think about them a little bit first. Then we'll come back together. Okay, so here's the warm-up. We're going to take 14 athletes competing in the final round of the Olympic luge event. So the idea here is how many different ways can the lugers, I'm not sure if that's one who luges, I'm not sure if that's actually how you say it, but can the lugers finish the competition? Assume there are no ties. And so the idea here is that we need to think a little bit about exactly how that's going to work. So yesterday we talked a little bit about factorial. This idea that essentially, if I think about the number of ways that, the number of possibilities rather for the first place to finish, there are 14 possibilities there. In order to find, to count in the second place people, if we've already picked one for the first spot, then there are only 13 more that could fill out second place, and so there are 13 left. And after we've filled the first two spots, now there are only 12 people to fill the third place spot. And that continues on and on until we get down to 1. And of course, we can shorthand that by saying 14 factorial. And if you punch that into your calculator, you get some ridiculously large number. I have this. I think I'm writing this down right. Good heavens. So something in the order of maybe 87 billion and some change. So a lot of different ways that we can order those athletes from first to 14th place. Question B says, how many different ways can the gold, silver, and bronze medals be awarded? And in this case, we're only really looking at the first 3 spots here. The rest of the folks, in terms of medals, don't really place high enough, and so we don't need to be considered. They don't need to be considered for that. So we have 14 athletes to take the gold, 13 left over for the silver, and 12 left over for the bronze. So that's 2,180 for that. Okay, so if we take a look at the question from Part B, so we'll kind of continue with the notes here. The number from Part B above is what we call a permutation. It's the number of permutations of 14 objects taken 3 at a time. It's denoted by this. So we're going to write the notation for this is, it's almost a subscript of 14 and then a capital P and then a lowercase or a subscript 3. So permutation is where the order is important. And of course, in this situation, the order is important because we're awarding somebody first place, somebody second place, and somebody third place. And if we were to just randomly give the top three, finishers a gold, silver, or bronze, that wouldn't be fair. The person that got the gold medal would feel ripped off, and so would probably cause a big fit. So the order that we award those is in fact important. Here's the way that we actually calculate that. So one of the ways that we can think about this is, we essentially started with, if we take a look at question A up here, we started with 14 factorial different possibilities. And really, if you think about how that relates to this question here, essentially what we've done is we have the same idea here, except we have, all the rest of this stuff is not included in the calculation because those places 11, starting at 11 to 10 to 9 to 8, all those don't matter as much. In fact, they don't matter at all for this problem. So notice what we've done here is we've taken this guy and we've really just divided out 11 factorial from it. And if we were to do that, then that would just leave us with this 14 times 13 times 12. And so, one way to think about that would be, well, what we did in the problem was we did 14 factorial divided by 11 factorial to get the rest of those factors out of there. A little bit more conceptually, using these numbers, we kind of did it, we really did it that way, right? We took out, the original 14 minus the 3 that are actually important, and that's what gave us the 11 factorial to begin with. And then, of course, if I bring this up here, if I had this, I could do 14. I wanted to write this out in extended form like we talked about yesterday. I could really bring that down to this so that the 11 factorials cancel out, and all I'm left with is this 14 times 13 times 12, which, of course, is the answer. So that's called a permutation, where the order is important. Again, taking a fixed number of things. In this case, we were taking 3 and ordering those 3 things from a larger group of 14 athletes in this case. Okay, so that generalizes or extends to a larger context, of course. Usually what we would see here is this idea here. So in general, the number of permutations of R objects taken from a group of n things, n distinct objects, is denoted by this. It's a subscript n, p, and then r. And again, n is the number of things that you're choosing from. R is the number of things that we're taking from that larger group. And the basic formula for that is this, that npr is equal to n factorial divided by n minus r factorial. And that's, again, kind of essentially what we did up here. If you think back to that example, hopefully conceptually that helps make sense where those numbers are actually coming from, but it does generalize to a larger formula. Okay, so let's take a look at 3 examples here, and then we'll take a look at one more idea. So a class has 26 students. In how many ways can the class elect a 4-person committee? And I'm actually going to change this. So I don't want to talk about a committee, but I want to say elect, let's say, a president, a vice president, a treasurer, and a secretary. Change the problem a little bit. Tomorrow in class, or actually probably on Monday, we'll get to talking about how we look at committees and how that's a little bit different. But this is essentially, looking at essentially the same kind of situation as the luge question, where there's one person for one position and another person for another position, and so on and so forth. So president, vice president, secretary, and treasurer. So we have 26 students here, right? And so this is a permutation because the order is important. Having a president, if I were the president of the class, that would be different than if I were the secretary or if I were the treasurer or the vice president. So all the order in which these guys are selected, or these people are selected, these students are selected, is really important. So from a group of 26, we're finding the number of permutations, the ordered values, when those are taken 4 at a time. And so if we put this into our formula from the previous example, then we have 26 factorial divided by 26 minus 4 factorial, which is, of course, 26 factorial over 22 factorial. a couple different ways you could do this. One is you could just put it into your calculator like that, and that's fine to do that. In fact, let's just do it that way for this problem. Get my calculator out here. Okay, so 26, remember our factorial button is down here. And then we divide that by 22 factorial. 26 factorial divided by 22 factorial. That's going to be about 358,000 and some change. So quite a big number of variety here. Big number of combinations, permutations here. All right, so let's go ahead and write that number back down in our notes. So that will end up being 358,800. So that many different ways to create those positions. If you want to take a look at question 2, a baseball coach is determining the batting order for the team. The team has 9 members, but the coach does not want the pitcher to be one of the first 4 to bat. How many batting orders are possible? Okay, so this one's a little bit trickier. We have to consider a couple different options here. And so definitely has 9 members, but the coach does not want the pitcher to be one of the first 4 to bat. Okay. So the idea here is if we kind of take the pitcher out of the mix for the first 4 positions, and really what we have 8 players to choose from. Again, 9 minus the 1 pitcher. And we want to find the number of permutations of the first 4 batters, right? So we have 8 players to choose from here, and we're choosing 4 of those players to fill out those first 4 slots in the batting order. And to that, we're going to take the remaining 5, so we're going to put the pitcher back in the mix. So now we have 5 players to choose from, and figure out the number of permutations of those last 5 slots. So how many ways, essentially, can I take all 5 of them out and order them in different ways? So this becomes the number, the calculation rather, that we need to do. So again, we can kind of put this in our calculators. Be 8 factorial over 8 minus 4 factorial times, and we do multiply here because any of the any of the permutations from the first one can be paired up with any of the permutations from the second part of the order. And here we'll do 5 factorial, and again, following our formula, we do 5 minus 5 factorial. Now, the interesting thing about this is we kind of talked about this a little bit yesterday, that 0 factorial, which is what the denominator here actually becomes, has to be equal to 1. That's an important definition, because if it were not defined that way, then this permutation formula would not work. And clearly what we're doing here is we're trying to figure out, well, if we take a look at the last 5 spots of the batting order, and we have 5 players to order within those 5 slots, then we say, well, position 5 of the batting order is there are 5 to choose from, and the 6th person in the batting order, there are 4 and 3 and 2 and 1. And so we know that this has to equal 5 factorial. However, according to this formula, if 0 factorial were not equal to 1, if it were equal to 0, like I think a lot of people thought would be the case yesterday, then that formula would actually fall apart, because this whole thing would end up being an undefined quantity, which wouldn't really help us with the problem. So to make sure that our permutation formula is valid in all situations where where we could use it, 0 factorial has to be equal to 1. That's one of the reasons why mathematicians chose to define it that way, just to stay consistent with the permutation formula. Anyway, so when I multiply all these together, finish this up here. When I multiply these together, then what I end up with, putting this in your calculator, is 201,600 different batting orders, which is a lot of possibilities, right? A lot of possibilities. Okay, so that's example 2. Let's take a look at example 3. All right, so in this case, slightly different problem, but it's not really a probability problem or counting the number of ways that things can happen, but it's more of an algebra problem in the context of this permutation formula. So we're actually trying to solve for n. What does n have to be on both sides in order for this to work? And so what we're going to start with is just rewriting each of these. We're going to take this and just rewrite it according to what the formula tells us it would be. It's n factorial on this side, n minus 4 factorial. This, of course, can be rewritten. This is 7 times n factorial divided by n minus 4 factorial, but that just means I can put that 7 up into the numerator because it's being multiplied by the whole fraction. And I like to do it this way for a couple different reasons. One of which is, in this next step, we can actually cross multiply. Okay, so what we end up with is 7 times n factorial when I multiply this way. 7 n factorial times n minus 5 factorial. And when I multiply the other cross product, I have n factorial times n minus 4 factorial. Okay, when you get to this spot, then I have n factorial on both sides, so I can divide that out. It's just the product of the same thing, so that does divide out. And then what I would like to do for this one is try to isolate the n, and it's really kind of tricky for this because that n is all wrapped up in the factorial thing, and those things just don't divide out very easily. I can't subtract n from both sides because it's wrapped up in the factorial notation again. So what I'm going to do is I'm going to suggest that we divide by n minus 5 factorial on both sides. And the reason that we would want to do that is that it gets us back into a somewhat familiar situation here where we have factorials on the top and the bottom. And yesterday we spent some time looking at those kind of problems. We had something like, I forget what our question from class was, but it was something crazy like, something like this. And we realized that if we could get this thing down to here, we could actually just express the rest of that product with the factorial. And what that allowed us to do is to cancel here and here, and we'd just be left with this. And so the same thing is going to be true for this question. We want to use that same idea, but we need to be a little bit careful about how we do it. Over here in this problem, notice that we start with whatever the factorial is, and then we subtract 1 each time that we peel off another factor. And so here, that same thing is going to be true, but what we're going to expand is the top. Because if I have n minus 4 factorial and I subtract 1 for that to figure out what the next factor is going to be, n minus 4 minus 1 is n minus 5. And I just leave it at that because that's exactly what is in the denominator, which is kind of where we want to be, because just like this problem over here, we really want that factorial to cancel out and get out of the way for us so that we can just get to the variable in this case. All right, so once we get here, again, these will cancel out, which is what we wanted in the first place, and we just end up with 7 is equal to n minus 4, which gives us n is equal to 11. All right, so if that didn't sink in, that's a pretty important idea. It's a little bit more abstract when we start working with variables here. So, if that didn't make sense, go ahead and replay that, listen to it a couple times, ask questions tomorrow, make a note of it. If you're not sure, I'll have the same set of notes up and ready to go when we start class tomorrow. A couple more types of problems here. So this question number 4 is kind of a piggyback off the problems that we did yesterday. How many distinguishable permutations are there for the letters that form the word mom? And so yesterday we did some problems where, I forget the exact problems, but they were of this nature of, how many kind of permutations were there for the word, I don't know, something like, something simple like dog, let's say. Okay, how many ways could we actually order those, that kind of way? We figured out that essentially what that was, it was 3 factorial. There were 3 letters to fill the first position, 2 letters to fill the second one, and then by the time we get to that last letter, there's only, we've already picked the first 2, so there's only 1 left. Okay, but this problem is a little bit different because it has repeating letters. And so if I had something like this, where I took M-O-M like this, but then I just reordered the first and the second M of that word, and I've underlined them here just to sort of show the difference. Those are essentially the same thing. And so if I say, well, this is 3 factorial, well, it's not, because 2 of those orderings actually result in the same word, M-O-M. It doesn't matter how I order this first and last M. They're still the same word. Okay, so when I have repeating letters like this, what I really need to do is to think about, well, let's look at just the repeats here. It's certainly going to start with 3 factorial because there are 3 letters, but the repeated letters, since there are 2 of them, there are going to be 2 factorial ways to order those. And so what I want to do is I want to take 3 factorial and divide by 2 factorial. And the 2 factorial, again, counts for the 2 repeated letters and the numbers of ways that I can order those. And so ultimately my answer just becomes 3. There are 3 distinguishable permutations. I could do this, and if I did this and reorder those, or I could do O-M-M and O-M-M this way. Again, putting underlines under one of those. Essentially these are the only 3 ways to order them in a distinct way, so they look like different words. The other ones are just repeats. Okay, so that also extends to questions like number 5. So if you take the letters of my last name, which there are 8, distinguishable permutations. Again, distinguishable just means that they're unique. They're not repeats. And again, since there are repeated letters in my last name, I'm going to have to divide those out. I'm going to take 2 factorial because I have 2 L's in my last name. And I'm also going to divide by 2 factorial because there are 2 I's. And that would, again, just like we did with the mom example here, that's going to uncount or divide out the number of repeats because of the way that those L's would be ordered. If we change my last name to, let's say I was Italian, and we changed my name to Silamani, then essentially I would have kind of the same idea, except now I'd have 9 letters. I'd have 2 factorial to account for the 2 L's, but now since there are 3 I's, I would divide out those 3 factorial I's, and again, that's the 3 factorial different ways to arrange those identical letters in the last name. 3 factorial because of the 3 I's. Okay, and essentially what that does is allows us to kind of generalize to this formula the number of distinct permutations of n objects where one object is repeated q1 times, another one is repeated q2 times, and so on. As we take, so that would be like my last name, 8 factorial, and then if I have q1 repeats for one of those letters, it'd be q1 factorial times q2 factorial times q3 factorial, however many numbers are repeated in this case, so I would divide out every single time, even if there are more repeats. And you'll have some problems for homework tonight where there are more than a couple repeats. That's the basic idea. You just divide out the repeats. Okay, so that is pretty much it. Just to remind you again to make sure that you go and finish up these problems. I think there are 8 problems there. We'll take a look at if you have any questions tomorrow, but that's pretty much it. And I look forward to seeing you all tomorrow. Take care.